Hey everyone, welcome back to the Cybernetters UNIX administration course. I'm Andrew Yick, and today we're going to be covering two essential admin tasks, printing and user management. These are fundamental to keeping a Unix system running smoothly. So today we'll cover things like different printing systems like BSD, SysV, and cups, and why cups is the most widely used today. We're also going to go through how print spoolers work, how print jobs are managed, and the common troubleshooting techniques. We're also going to be understanding how user authentication passwords and system accounts and how Unix stores user information. We are going to also talk about how to add, modify, and remove users and groups and setting this limits on disk usage and for users and enforcing these security policies. We are at last also going to talk about how Unix extends authentication just beyond passwords. So by the end of this video, you have more knowledge to how to manage users, configure print services, and making sure that you have secure access to the system. So let's get started. So in Unix and Linux, there are three main approaches to printing, which each with its own history and use cases. So first we have the BSD style of printing, which uses the LPD and LPR, or its newer version, LPRNG. This approach originated in BSD Unix and is still supported by many networked Ethernet printers, but it's not as commonly used today as the other system. We also have the SysV style of printing, which comes with from the System V Unix. It was once widely used, but today it's mostly obsolete. You might still encounter it in legacy systems, but for the most part, it has been replaced. And finally, we have CUPS, or the Common Unix Printing System, which is the modern standard or the one that we use today. CUPS is widely available on Unix and Linux system, and it supports a broad range of printers. It is the default printing system on most distribution and even on macOS. It handles print jobs efficiently, support network printing, and is actively maintained. So while the two older versions, which are BSD and SysV printing, still exist in some environments, CUPS is the way forward for most Unix and Linux systems today. So let's go deeper into the components of printing in Unix and Linux. So this involves two key components, which is the print spoolers and the user level utilities. So the print spooler is responsible for collecting, queuing, and scheduling print jobs. The term spool stands for simultaneous peripheral operation online, which is basically means that instead of sending the print jobs directly to a computer, they're queued up and processed in order, which allows multiple users to print effectively without conflicts. Then next we have the user level utilities, which are the tools that let users interact with their printing system. They can be command line utilities or graphical interfaces that allow users to send the jobs, check their status, cancel or reschedule jobs, or change printer settings. So behind the scenes, these utilities can communicate directly with the printer and can even transfer print jobs between different spoolers over a network, which ensures the smooth printing operations across multiple systems. So here is a diagram of what I'm talking about, which, as I mentioned before, is what manages the printing on most Linux Unix systems. So think of it as like the middleman between you and your printer. So first, you send a job using a command like LP. This is like hitting the print button on your computer when you like want to print a document and then you press the print button. In Linux, it's like using the command LP. So, and then cups then decides what to do with the job. It either accepts it into the queue if everything is good, or it rejects it. So, like if there's an issue, it rejects it, like the printer being offline. Also, then the print job waits in a queue at the file bar spools cups until it's ready to be printed. The queue then makes sure that multiple users can send jobs without it being messy. Cups sends the jobs to the printer. but only if printing is enabled. If printing is disabled, the job just sits there until the printer is then enabled. And then finally, the printer just prints the job, which completes the process. So, in summary of what I talked about, cups is like the boss, which decides when and how a print job reaches the printer. It makes sure that everything is queued properly, so it prevents a chaotic print war in the shared environments. So, as we mentioned before and established that, cups is the standard printing system for Unix-like operating systems, which includes Linux and Mac OS. It was acquired by Apple in 2007 and it supports a wide range of printers. So, some key features is that it has a built-in web interface which you can access at HTTP localhost port 631 for easy setup and management. It also supports the USB printers but requires them to be powered on before setup. It also includes various print drivers for compatibility and it's maintained independently, which ensure broad support access across different systems. So, in short, cups is the go-to solutions for managing printers in Unix-based systems. So, as we mentioned in the previous videos, everything in Linux is managed as a file. So, even cups. So, cups has two main configuration files. First one is the server configuration, which is found in etc cupsd.conf, which controls the printer setup, which includes the driver and the connection type. It also defines the access permissions, which allows or restricts printing based on IP and other rules. We also have the client configuration, which is found in etccupsclient.conf, which is used to connect a system to a remote cups print server, often unnecessary if the server is within the permitted IP range and advertises itself automatically. So, in summary, the server config controls the printer while the client config helps connect to the network printers. Cups includes its own version of traditional BSD printing commands like LP, LPR, LPRM, and LPRQ, so scripts using these commands will still work as expected. However, if both BSD printing and cups are installed, their order in the system's path can cause conflicts. So, to avoid these issues, it's best to stick to one printing system per machine. So let's talk about how you can set up cups on your Unix system, which involves a few key steps. So the first one is to obviously install cups using your packet manager, like it could be DNF, yum, apt, etc. The second step is to start and enable the cup service with sudo system start cups or to stop it, sudo system stop cups. And then you check the available printer drivers with lp-info-m and then you add a printer using the lpadmin-p command. You then monitor the print status using lpstat-a and then you submit the jobs using LPR. So if handling text files from Windows, you convert the line endings using DOS to Unix to prevent the formatting issues. So when printing problems arise, here's how you can diagnose and fix them. So the first thing is you can start by restarting the print daemon. So like if a job is stuck and it's not processing, you can restart the print service and it will often resolve it. If that doesn't work, you can check the log file. The logs for here are stored under var/log and can provide error messages and insight into what's wrong. The log level can be adjusted in etccupsd.com. So if you have issues with the network printing, you can also use their web interface. So you can access cups at http://print server colon 631 to check the queue status. You can also check the client side, which includes stuff like checking the network settings, their printer permissions, or the missing definitions. You can also look into server-side issues such as looking for incorrect device names, driver issues, or job transmission failures. And you also have the pre-processing errors, which if the files won't print properly, you should ensure correct formatting with the program mentioned before, the DOS2 Unix. So if you're troubleshooting network printers, always check the IP resolution and firewall settings to make sure your jobs aren't being blocked. Alright, let's talk about the user and group administration in Unix. Now, when we're dealing with user accounts, there are two key files that you need to know. First up, we have the etc password, which is where the system keeps track of the user accounts. Things like usernames, user IDs, group IDs, and home directories. But here's the catch. It is readable by anyone on the system, which is a huge security risk if passwords were stored here. Next, that's why we have etc shadow. This is where the real password data lives. It holds the encrypted passwords along with the expiration dates and other security-related info. The cool part, not only root can read this file, only root can read this file, which makes it more secure. And then now, about password encryption. Unix doesn't store passwords in plain text, obviously. It uses salts, which is random two-character values that add to a password before encrypting it with DS hashing. This makes it harder to crack since even if two users have the same password, their hashes will be different. So, what happens if you need to switch between these two password storage methods? pwconf moves password from etc password to etc shadow, which makes the system more secure. pwconf does the opposite. It disables the shadow passwords and it moves them back to etc passwords, which honestly is a bad idea unless you have a specific reason. So the bottom line is to stick with etc shadow, which makes your system way more secure. So let's talk about password expiration settings in Unix and how they keep your system secure. So now everything related to password expiration is stored in etc shadow, which, like we talked about earlier, only root can access. This file keeps track of when and how often users need to update their passwords. So minimum sets the minimum amount of days a user must wait before changing their password again. It is there to prevent users from constantly cycling through old passwords just to reset back to the original. Max defines how long a password can be used before a system forces change. If the number is reached, the password expires and the user has to update it. Warn is the warning period. Before the password expires, the system will start nagging the user's reminder. Hey, your password is about to expire. Change it before you get locked out. Now, let's say a user doesn't change their password in time. This is where grace period comes in. Even if the expiration date passes, Unix gives them a set number of extra days, which is defined in the disable field, to log in and update it before their account gets completely locked out. Now switching gears, let's talk about the etc group file. This is basically the group version of etc password. Instead of tracking the individual users, it tracks the groups and their members. Each entry in the file contains the group name, the group ID, or the GID, and it also contains a list of all the users who are part of that group. Groups are super important in Unix because they control shared access. Instead of giving permissions to every user, you just assign them to a group, and boom, everyone in that group gets the same access. The etc password file contains 7 key fields that defines the user account on a Unix system. Each field is separated by colon and they provide details like the name, which is the actual username, coded password, which is a placeholder X since real passwords are stored securely in etc shadow. And then you have the UID or the user ID, which is a unique number assigned to each user. System accounts are usually under 100, by the way. GID or group ID, which links the user to a group in etc's group. And then you have the user information, which is typically the full name of the user, but not always required. And then you have the home directory, which is the default directory the user lands into after logging in. Like, for example, home username, and then shell, which defines the user login shell, like the bin bash. This file is very important for managing users, but passwords aren't stored here anymore, which is used which are moved to Etsy Shadow for security reasons. Alright, so here is a sample Etsy password file. I'm not going to go too in depth in it, but it basically stores the user account information. So each of these lines represent a user with fields separated by colons. So as you can see, the root user has UID 0 or full system control, and then the daemon is the system service accounts, which is not actual users. The LP is that handles the printing services. The nobody is a restricted user with no permissions, and then the AYIC is the regular user with a home directory and slash bin bash is the cell. Just notice how the password field is always X. That means real passwords are stored securely in Etsy Shadow. So let's go over standard users in the Unix system. First up, you have root, which is the super user, full system control. You don't want to mess with this one unless absolutely necessary. Next, we have the daemon, which is used to run background services, things that don't need a real user to log in. And then you have bin and sys. These are its own important system files and utilities. And then you have ADM, which handles the system accounting logs. And then you have UUCP, which is an old school file transfer system, which is not really used today. And then we have the service accounts like cron, mail, and LP, which runs specific tasks like scheduling and printing. And then you have auth and audit, which is used for system monitoring. And then finally, you have nobody, which is the guest account of Unix, used when a process shouldn't have any real privileges. These users keep the system running behind the scenes, and most of the time, you don't need to interact with them directly. Let's talk about creating user accounts in Unix. We use useradd or add user on some systems to create a new users. But where does it pull its settings from? Etsy login.defs is the file that defines the system-wide policies like password rules and UID/GID ranges. And then you have the Etsy default user add, which sets defaults like the user's home directory, shell, and primary group. And then you have the Etsy scale, which is the skeleton directory, meaning files here are automatically copied into every new user's home directory. If you need to override these defaults, you can add extra options to the useradd command. And don't forget, after creating an account, you need to set a password with passwd. Now, what if you need to modify or delete a user account? Usermod lets you update user details, like changing the home directory or the group membership. Chage adjusts password expiration settings so you can't force users to update passwords after a set time. If you need to prevent a user from login, use usermod-l username or password-l username. Another trick is changing their shell to a non-interactive one with chsh, making it impossible to log in manually. Userdel username removes the account, but the user's file still exists, just owned by their UID, a number. If a new user is created with the same UID, they could inherit those files, so be careful. Always double check before deleting a user. You don't want orphaned files floating around. Managing groups in Unix is just as important as managing users. You can manually edit the Etsy group or use group apps to create a new group. Need to rename a group or change its ID? You can use group mod. To remove a group directly or entirely, you can use group del. Groups list all groups you belong to. ID shows your user IDs and group IDs so you know exactly where you stand. New GRP lets you temporarily switch your primary group. This affects file ownership when creating new files. This is crucial for organizing user permissions effectively. This quotas help manage storage by setting limits on how much space each users and groups can use. So modify Etsy tab to add user quota and GRP quota options for the system to enable quotas. And then to remount the file system, you can use mount-o remount and then the mount point to apply the quota settings. To create the or to initialize the quota files, you create the quota database and scan disk usage with quota check -cug mount point. And then to assign the quotas, you use add quota -u and then the username to set user limits like 800 megabytes of soft and then 1 gigabyte of hard limits. It prevents all the users from taking up all the space and keeps storage under control. So PAM or pluggable authentication modules is like the middleman of authentication on Unix systems. Instead of applications having to handle authentications themselves, they just ask PAM and PAM does the heavy lifting. So user credentials are stored in files like etc password and etc shadow, where the Unix system manages authentication data. PAM provides flexible authentication system which allows different methods like passwords, biometrics, radius authentication, or even two-factor authentication. So applications don't need to worry about authentication details. They'll just all call PAM. PAM then decides which authentication method to use based on system administrator settings. It allows administrators to configure security policies without modifying individual applications. So think of PAM as the security checkpoint kind of. When you log in, it verifies your identity and whatever authentication methods are set up, whether it's a password, fingerprint, or network-based logged in. So PAM follows a simple format: module type, control flag, model path arguments. So each line in the PAM config determines a specific authentication step. So auth handles the authentication, which is the password validation. Accounts checks if the user is allowed to log in, such as the password expiration. Session manages the session activities like creating the home directories, and password handles the password management and complexity enforcement. Basically, PAM processes these modules in order, deciding who can log in and if they're allowed and what happens when they do. So PAM or pluggable authentication modules is like the middleman of authentication on Unix systems. Instead of applications having to handle authentications themselves, they just ask PAM and PAM does the heavy lifting. So user credentials are stored in files like etc password and etc shadow, where the Unix system manages authentication data. PAM provides flexible authentication system which allows different methods like passwords, biometrics, radius authentication, or even two-factor authentication. So applications don't need to worry about authentication details. They'll just all call PAM. PAM then decides which authentication method to use based on system administrator settings. It allows administrators to configure security policies without modifying individual applications. So think of PAM as the security checkpoint kind of. When you log in, it verifies your identity and whatever authentication methods are set up, whether it's a password, fingerprint, or network-based logged in. So PAM follows a simple format: module type, control flag, model path arguments. So each line in the PAM config determines a specific authentication step. So auth handles the authentication, which is the password validation. Accounts checks if the user is allowed to log in, such as the password expiration. Session manages the session activities like creating the home directories, and password handles the password management and complexity enforcement. Basically, PAM processes these modules in order, deciding who can log in and if they're allowed and what happens when they do.